Okay, so hi everyone. Today we'll be discussing this problem K good trees. So it's of a contest of from Hackerearth. It's of June circuits. The contest is currently running. So the problem goes something like this. A tree is called K good if all the nodes of the tree have exactly K children except the leaves for a given count of leaves. So they'll be giving you the count of leaves and the tree is actually K array. As you can see, it has exactly K children. Every node has exactly K children and they'll be giving you the leaves and you have to answer all the possible values of k. So I'll just explain with a small example what they mean to say with this. So let's just say I'll be constructing a tree, something like this. So in this case, as you can see, the value of k is 3. Why I'm saying that the k is 3? Because every node except the child node, sorry, except the leaf node, all of them have 3 children. And for in this case m is actually equals to 5 because you have a total of 5 leaves, right? You have a total of 5 leaves, so m is actually the number of leaves and k is the how many nodes each node has, sorry, how many children each node has, how many child each node has. And yeah, so basically k is equals to 3 means how many child each node has except the leaves, because obviously their leaves they cannot have a further extension. So if you are asked for m is equals to 5, one answer is obviously k is equals to 3. And let's try to make another one. This is another configuration. Here, as you can see, again, there are a total of 5 children of the root node. So again, this satisfies. So k is equals to 5 is again an answer to your solution. And let's just try again for k is equals to 2. Let's just see that if we can get 5 leaves. So let's try that. Yeah, so as you can see, I have a total of 5 leaves and the value of k for this tree is equals to 2 because every node except the leaf node has exactly 2 children. So again, k is equals to 2 is an answer. So there may be many possible answer, or I think this is it. 235 is the only possible solution. Yeah, I think then you have to answer 3 for this. So this is basically the question. This is the brief idea of the solution, but you'll be given m and you have to answer all the possible values of k. So let's just solve this question, but while solving the question, we'll be looking this question in a reverse way. We'll be checking for value for k is equals to, let's just say, 3, what all values of m are possible. We'll be solving the question in this way. So let's just say if this is the case, let's just say for k is equals to 3, right? So k is equals to 3 has this is one case. As you can see, the value of m here is equals to 3. If I extend this tree, like if I increase the depth, keeping in mind that every node should have 3 children. So this is how the extension looks, and you can see the value of m for this tree is 5. Again, if I extend this, keeping in mind that k is 3, so this is the extension 1, 2, 3, 4, 5, 6, 7, 7. So you can see a pattern over here, but this is what we'll be doing. This is how we'll be solving the question. So let's just directly get into that. So let's just say we'll first do a dry run on k is equals to 3. So for k is equals to 3, let's just make the most skeletal structure. This is the first skeletal structure. So what is the value of m over here? The, I'll be also making m3. What is m3? M is 3 means what all values of m are possible considering that the value of k is equals to 3. So m is 3. So how many leaves do you have over here? You have 3. So that's a first value. You cannot get a value lesser than that. That's not possible. This is a basic skeletal structure. So again, if I try to extend the tree, let's extend it. I'll show you why we are getting that pattern. So 1, 2, 3, 4, 5. So this is 3, 5. Again, let's extend it a bit more. Um, 1, 2, 3, 4, 5, 6, 7. As you can see, we have an AP of 2, but I'll prove it to you why we are getting an AP of 2. Let me just show you that it is working for all the cases. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this continues to increasing, like this keeps on increasing. Now let's just say we are trying for k is equals to 4. So let's make the skeletal 1, 2, 3, 4. This is how it looks. So what is the first value that we get? 4. Now again, if I try to extend it, 7. Here you can see it's not 2, it's 3. So why it's changing? But you are seeing that we are always seeing a pattern when we are solving for one single value of k. So again, if I extend it, it's simple. Again, increment of 10, increment of 13, increment of 16, and it goes on. Again for M5. Now I'll be explaining you why we are getting the pattern by like after taking the example of M5. So let's try for K5. Let's try for K5. So this is the skeletal. So as you can see, the skeletal is always this only, and the first element is always k. Like if you have taken k is equals to 5, the first element of M5 is always going to be 5 only. Now, if you see what I have been doing till now, I am attaching children under the, you can do it anywhere, but I'm just doing it for a simple implementation. I am attaching children below this node. So this particular node is no more the child, is no more a leaf, so there is always a minus 1. So whatever value we had, this is the old value, right? So old value minus 1 is always there because whatever all the leaves that were present previously in the old structure, this is the old structure where we'll be making the new structure. There will be a minus 1 because you will be attaching 5 children below this. So minus 1, but you also added 5 children, right? So plus 5. So this is the common difference. This, okay. Okay, so this is the common difference. So again, minus 1 plus 5, the common difference becomes 4. So 5, 9, 13, 17, 21, 25. This continues. And if you clearly observe, the D for this was 2. D for this was 3. D for this is 4. Why it is 4? It is always this pattern minus 1 plus k. So D in standard. So D standard, matlab, I mean general. D general is always k minus 1. This is how it is. D standard is always k minus 1. That that will always be the common difference. So I'll just revise what I'm doing over here. I'm solving for k is equals to 3. What all values of m are possible? This is not the question, but this will make the implementation way easier. Like it's a 4 to 5 line code then. So this is what you have to see K3, K4, K5, and you'll be seeing an AP for all of them. So now let's now actually get into the question, like what the question was trying to say. I hope you got why we are getting the dk minus 1, because it's always removing a node, adding 4 nodes. Not removing actually, like taking the leaf ownership of the node, you can say, because that tree, because that particular node will no more be the leaf in which you are attaching the children. You are attaching children below a node, right? So that node is no more a leaf, but the new children are the leaf. So minus 1 plus k, because you always have to add k children only. So k minus 1 becomes always the common difference. So now this is how the series looks. But now if I ask you what was the question was you'll be given a value of m, and you have to answer in, like if I ask you m is equals to 7, you will become going to m3, you will be saying okay, we have a 7 over here, count plus plus. Suppose count is your answer, we have a 7 over here, count plus plus. And for m2 also, like if I just make it for m2 also, it is much simpler because the common difference, as you can say, it's 2 minus 1. So 2, 3, 4, 5, 6, 7. Okay, 7 is also, look, 7 is here also, so again count plus plus. And also 7 would obviously be in M7 also. The first element we said. So again count plus plus. And then you'll be returning the answer as 4. So basically in the dry run I just did, you are checking for how many series are we getting the answer. So now let's try to generalize every series. So let's just say we have taken a random value k. We don't know actually what all values of k. We have to solve that. Like for what all values of k will be, like we'll be getting um the m value m7. So if I generalize, every series starts something like this. The first value is k, and then k plus k minus 1 times some value x. This is it, right? Like for suppose 17. 17 is 5 plus 5 minus 1 times 3. That is 7. So basically AP. AN is equals to A plus N minus 1 T. Then again 5 plus 5 minus 1 times 4. That will give you 21. So as you can see, this is the common structure. This is the structure. Like this will give you element X, suppose. This will give you the element X, but you don't have an, like you're not given K in the question, you're not given X, but you can say that K plus K minus 1 X is equals to M. You are given M. Now the question is complete mathematical. How many solution exists for this particular equation? How many values of K are possible for this particular equation? That is your final question. Given the equation K plus K minus 1 into X equals M, how many values of K are possible? So let's solve this right now. Okay, so I'll be erasing everything. So if we again write that K plus K minus 1 times X equals to M. Now I'll be solving this and I'll be showing you how many values of K are possible. I hope you got why this equation we got. It's a simple AP, but we are not familiar of the first term. We are not familiar of the common difference. We just know that it's K minus 1. So if I solve this, let's just take everything to RHS. We'll be only keeping X on the LHS. So X is equals to M minus K divided by K minus 1 uh, minus of K minus M divided by K minus 1. Just add a minus 1 plus 1 inside it. Plus 1 minus 1 K minus 1 uh, K minus 1 minus M plus 1. I hope I'm writing this fine. This becomes K minus 1. Okay, I'll be continuing over here. Then X is equals to now you can simplify it much more. Minus K minus then I'll be taking the minus inside. Then it becomes plus M minus 1 divided by K minus 1. X is equals to, just split this thing, like split the numerator. So minus K minus 1 divided by K minus 1 plus M minus 1 divided by K minus 1. So this will give you minus 1 plus M minus 1 K minus 1. This is the final equation. Now this makes your solution much more easier. Now you have to find the integral solutions of X. That's the solution, right? Integrals have, like, what all values of X. You don't know X actually. X is a variable. So what all values of X are possible? That is exactly equals to the number of divisors of M minus 1. X is given. You have to find the solution. How many values of X are possible? So all you have to do is find the divisors of M minus 1 and you are done. For example, it's M minus, so for example, M was, let's just say M is 8. Like, why I'm showing this? Like, find the divisors of M minus 1. That's the complete question. Suppose in the previous question, M was given 7. If you just rewind, you'll see that I think we had 4 as the answer for 7. It was in 2, it was in 3, I think it was in 2, 3, 4, and 7. So if I take M7, then X is equals to minus 1 plus 6 by K minus 1. Now what do you think all, like, what can we put, like, what all values of K can we add here? We can add 2, we can add 3, we can add a 4, and we can add a 7. So this is the complete question. Find the divisors of M minus 1. You'll be getting the integral solutions, and that was the whole question. So the complete question boils down to find divisors of, I think this part would have been cut. I'll just write this thing again. For example, um, m is equals to 7. M is equals to 7, right? So if I rewrite this particular equation, it becomes X is equals to minus 1 plus 6 by K minus 1, right? So what all values of K do you think we can add over here? We can add 2, 3, 4, and a 7. So all you have to do is find, like, why did I add 2? Because 2 minus 1 is 1, and 6, like 6 by 1 is an integral. Why did I add 3? 6 by 2 divisible. Why did I have 4? 4 is not divisible, but 4 minus 1, 6 by 3 is will give you an integral value. Why did I have 7? 6 by 6, k minus 1, right? 6 by 6 will give you the answer. So the complete question boils down to find divisors of m minus 1. And then it is a simple question. Like, if you know that, like, if you got into this conclusion, then it becomes a very simple question. So this is my solution. Like, if you still need the solution, you must be familiar with the common, like the common standard algorithm, like root n algorithm to find the divisor of something. So I won't be explaining this code. Like, you can find GFG links also related to this, how to find divisors of a number in root n. You just basically, like, for example, I want to find the number of divisors for a number n. So you traverse till root n. You always traverse till root n, count, and then you also keep a check on the RHS also, like the other side of root n, because those will be also counted, right? But it will be handled, so you don't need to like 3 into 4 is 12, but we are only traversing 3, and we are adding 4 also. Like, here we'll be adding 4 also. So if you uh, just read this, like, it's a normal, pretty, like a very, like very frequently used algorithm. So yeah, like, this was the question. The only observation needed was that series, like why we are getting that series, what is the common difference of that series. Once you have got that, write the general equation of all the series. It is always k plus k minus 1 x. Once you have written the common difference, equate it to m, because you wrote the equation for a term, right? Tx is equals to k plus k minus 1 x. And then after equating it, you have to find the solutions. So if you just rearrange, you can see in the video, if you just rearrange, you can see that it, in the end, it comes down to a division that has to turn out as an integer, and for that you have to find the divisors of the numerator. That was the whole question. Thank you.